Hi everyone. Today let's talk about section 10.1, parametric equations. Big idea. Points on a graph can be represented by two separate equations for the x and y coordinates in the terms of a third variable, usually called t, instead of a single equation. The variable t represents times in many applications, which make parametric equations useful for describing the location of objects as a function of time. Find the slope of tangent lines and the area at length enclosed by a curve described by parametric equations requires slightly different formula than we had for f of x, okay? Big skills. You should be able to recognize and easily graph the parametric representation of some common curves like lines, parabola, circles, and ellipse. You should be able to calculate the first and second derivative of a graph defined by parametric equations, the area and arc length for a closed graph. Okay, so the three applications we need to know is how to calculate the derivative, and how to find the area, and how to find the arc length. Okay, so those three important applications for the parametric equations. So suppose that x and y are both given as functions of a third variable t. We call it a parameter by the equations. So now you have x and y, they are both functions of t, okay? We call this parametric equations. Each value of t determines a point, xy, which we can plot in a coordinate plane. As t varies, the points varies and chase out a curve. So we call this curve a parametric curve. Okay, so actually parametric equations give us more information than the regular curve, okay? Because at a different time, we can know like when is the point travel and what, at a particular time, where is the point, where's the location of the point. And we can also know the direction of the point traveling, okay? It's like a forward direction or backward direction. Okay, so parametric equations actually tell us more information than the regular functions. Okay, so in this session, so we have two big concepts. Okay, so we have parametric equations. So x is a function of t and y is a function of t. Okay, we can also have functions, okay? So functions like y is like a function of x, okay? So given a parametric equations, how do you get a function? Or sometimes instead of functions, we might not have a function, then think about xy relation. Okay, which is a function involving x and y. Okay, so given a parametric equation, how do we get a function, xy relation? Okay, or given a function between x and y, how do we get a parametric equations? So let's figure out this. So example 1, we're given the parametric equations. How do we find the function or the xy relation and identify the curve defined by that? Okay. X equals to cosine t, y equals to sine t. Well, think about that. What's the relation between sine and cosine? Well, the trig identities, right? What's the relation between sine and cosine? We know sine over cosine is tangent, and there is a trig identities involving them. Well, that is cosine squared plus sine squared equals 1. Right? So we plug in cosine is x. Well, x squared plus y squared is 1. What is this guy? This is a circle centered at the origin and with radius. What's radius? 1, right? And so this guy is a unit circle. So let me draw it. Okay, so this guy is the unit circle. Let me draw better. Okay, 1, 0, 1, minus 1, minus 1. Okay, so this is a unit circle. At time t equals 0, where is the point? X is cosine t, so cosine of 0 is 1. Sine 0 is 0. So at t equal to 0, we actually at this point 1, 0. Okay, and then when t equals to pi over 2, cosine pi over 2 is 0, sine pi over 2 is 1. So we're actually at the points 0, 1. So this is when t equals pi over 2. And then you realize when t equals to pi, we're at the points minus 1, 0. And when t equals to 3 pi over 2, we're at the points 0, negative 1. And when t equals to 2 pi, we get back to the points 1, 0. So you can see the trajectory. So this is the trajectory of the points, and the point is traveling, this is counterclockwise. So far, so good? Okay. And so this is the curve. The curve is a circle. What is the standard form for the circle? Well, the standard form for the circle is x minus a squared plus y minus b squared equals to r squared. And the center is AB and the radius is r. Okay, so this is the circle. So far, so good. So given the parametric equation and we find the xy relation. So this is the xy relation. It's not a function, but it's a relation between x and y. All right, let's continue. Okay, example 2, we have x equals to cosine 2t and y equals to sine 2t. What's the relationship between them? Still, no matter what angle it is, cosine squared plus sine squared is 1. So we also have x squared plus y squared equals to 1. That is still a unit circle centered at 0. Okay, so let's draw it. Okay. Alright, so we still have a unit circle. Okay, so at t equals to 0, we have 1, 0. Okay. And when t equals to pi over 2, cosine pi over 2 times 2 is pi. Cosine pi is actually negative 1. So actually, we get t equals pi over 2, we get this point. And when t equals to pi, we get back to this point 1, 0. And when t equals to 3 pi over 2, we get to the point 0, 1. And when t is 2 pi, we get to this point again. So what happened with the points? Well, it actually wraps the circle twice. Okay, it wraps around once. And it wraps around one more time. So it wraps around twice. Okay, and this is a picture. And you can see as the curve, you can see the curve is still the same. So example 1 and example 2, you can see the curve is still the unit circle. But example 2 is double speed. Okay, so compare to example 1. Example 2 is double speed. Okay, and it goes around the circle twice. Okay, it goes around the circle. This is counterclockwise and twice. So far, so good, everybody. Okay, so there are still examples about given the parametric equation, how do we find the xy relation? Okay, let's continue. Example 3. All right. Whoa, still have cosine and sine. So then it's the same trait identities. Cosine squared plus sine squared is 1. But what is cosine? Well, cosine t is x over 5. Sine t is y over 2. And because cosine squared plus sine squared is 1, then we have x over 5 squared plus y over 2 squared equals to 1. So we have x squared over 25 plus y squared over 4 equals to 1. What is this guy? This is actually ellipse. Okay, and how do we draw ellipse? Well, let's use this to draw the xy coordinates. Okay, so here you can see the standard form for ellipse is x squared over a squared plus y squared over b squared equals to 1. So if a and b are the major or minor axes depending on which one is bigger. Okay, so in this case, a squared is like 25, so a is 5. B squared is like 4, so b is 2. So the major axis is on the x-axis. So that's why here, 5 right here. And 2 there. Okay, so we have major axis on the y-axis and then the minor axis on the x-axis. So we connect those points together. So we get ellipse. So at time t equal to 0, x equals to 5 times 1. So 5, y equals to sine 0 is 0. So we are at the point 5, 0. Okay? And then when t equals to pi over 2, cosine pi over 2 is 0, sine pi over 2 is 1. So we are at the point 0, 1. And when t equals to pi, we're at the point negative 5, 0. And when t equals to 3 pi over 2, we're at the point 0, negative 2. Okay? So now you can see the point is traveling, when t increases, is also traveling counterclockwise along the ellipse. Okay, so here the xy relation, this is the xy relation, and we have the ellipse. Okay? Alright, let's look at example 4. Sketch and identifying the curve defined by parametric equation. Well, here we want to get rid of the t, right? So how do we get rid of the t? Well, we can use substitution, right? Substitution method to get rid of the t. So here you see t squared. Well, when you solve for t here, it involves square root, so that's hard. But here we have t, so let's solve for t here. So t is then x equals to 2, then plug into the second equation. So y equals 1/2. T is x over 2 squared minus 4. So that is x squared over 2 squared is 4 times 2, 8. So our equation y equals x squared over 8 minus 4. This is a parabola. Oops. Okay, how do we graph it? Well, we know that so the leading coefficient is 1 over 8. That's positive. So we have parabola open up. Okay. And let's put some points. So here, because t goes between 0 and 8, okay? So because t is x over 2, then x over 2 is between 0 and 8. Well, when we solve for x, we multiply by 2 on each term. So we have x is between 0 and 16. Okay, now let's see. When x is 0, we get what? Negative 4. Let's say this is negative 4. So we're right here. When x is 16, well, 16 squared. Let's see, 16 squared divided by 8. minus 4. We get 28. So when x is 16, we actually get 28. So we know it's a parabola, so let's connect them smoothly. Okay? And this is when t equal to 0. This is when t equals to 8. Okay? And this is the piece of the parabola. So far, so good, everybody? Okay, let's continue. Example 5. Find a parametric representation of the following curves. So, example 1 to example 4 is about given the parametric equation, how to find the xy relation or function. Example 5 is the reverse order. We're given the function or xy relation, and we want to get a parametric equation. So you can see one function or one xy relation, we can have many different parametric equations. Okay, we can have double speed. Right, so let's look at the first one. Okay, so you can see first one, y is a function of x, right? So here we have some natural parametrization. Okay, so if y is a function of x, the natural parametrization is, well, because x is the independent variable, we let it be t, then the y is the dependent variable, just f of t. Okay, so this is a natural parametrization. If we have x is a function of g of y, then we let y to be t, and then x is just going to be g of t. So here are the natural parametrization. Okay, so let's see. So I want to give you more examples of parametrization. So the first one, okay, we can use the natural parametrization because x is the independent variable. We let x be t, and then the y is 9 minus t squared. And x is t, then we have t is between 1 and 3. Okay, so that is the natural parametrization. Well, can we let x be 2t? Yes. Then the y is 9 minus 2t squared is 4t squared. Okay, but you gotta be careful because minus 1 less than or equal to x. X is 2t. Then t is between minus 1/2 and 3/2. You see the range of t changes here. Okay, and you can see the parametrization number 2 is double speed of the first one. Can we make more interesting? Can we try t cubed? Yeah, of course. Well, then your y is gonna be 9 minus t cubed, and to the second is t to the 6. And then we have, because it's x, is t cubed, is bounded between minus 1 and 1. When you take the cube root of -1 is still -1. And then we have the cube root of 3. You see the range of t changes. Okay, how about can I try x equals square root of t? Oh, then y is 9 minus square root of t squared is t. Oh, and then, but what happened? Well, square root of t, and that is around 3, right? So when you, because the square root, the t has to be bounded between 0 and here 9. So actually, this is not good. Why is that? This is not good. This is not a good parametrization. Okay, this one is not good. Because you cannot reach the pieces for when your x is less than 0. Okay, the smallest you can reach is 0. So if we want to draw the picture, illustrate what happened here. So 9 minus x squared. Well, 9 minus x squared, this is 9, and this is 3, and minus 3. 9 minus x squared is like this. Okay, and x is between minus 1 So let's see, -1 is here. So we're actually on these pieces. So at -1, 2, 3. Okay, so we're actually on these pieces. Okay, but the number 4, the number 4, if you choose this guy to be a parameterization, you can only include the pieces from here. I don't want to use the red because it's hard to see the difference. So this guy is not good because it only covers the pieces from here to here. It cannot cover the pieces from -1 to 0. So this is not a good parameterization. We have to be careful with that. Okay, so let's continue. Part B. Part B, we have x is a function of y. Then, well, we use the natural parameterization. Let y be t, and then x is t minus 5 squared plus square root of t. And here it means because square root y, then y has to be greater or equal to 0. So here the t is greater or equal to 0. So far, so good. So this is how we're given functions or xy relation, and how do we find the parameterization for it. Okay, let's continue. So the path of a light on the rim of a rolling wheel is a cycloid, which has the parametric equation. So this is a parametric equation, and you can imagine if you're riding a bike, and then you're riding a bike here. Okay, so you're riding on a bike, and a gum sticked on your bike. So a gum stick on your bike, and what happened gonna look like the gum. So your gum will actually look like the trajectory of your gum travel. It's actually like the red curve. Okay, and this is a cycloid. And the parametric equation is x equals to a t minus sine t, y equals to a times 1 minus cosine t. And in this case, when we're not able to express the parametric equations in terms of an xy relation. Okay, so actually the parametric equation is like more general. Okay, it can help us to define more general function. So if you want to draw a category, so functions is smaller than the xy relation. Okay, so we have the function here. We can use the y is a function of x, or x is a function of y. We can always express using parametric equation. But however, there are some parametric equation that we're not able to get a function from it. Okay, so the parametric equation is bigger than the function. It contains the function. Function is like a smaller subset of that. So far, so good, everybody? Okay. Example 7, the path of a point on the circle A with radius a over 4 that rolls on the inside of a circle B with radius a is a asteroid or hypercycloid. Its parametric equation are this. Okay. Have you played with some spiral graph? Like you have a bigger circle, and then you have the small circle, and then you go around, and it generates so beautiful shapes. So yeah, if this kind of reminds you what you did before, yeah, it's amazing. And cycloid is let me see. This picture is one of them. Okay, so you actually get this picture. Okay, so are we able to express this in terms of xy relation? Let's try to do that. So here we get, we can solve a cosine. So what's cosine? Well, cosine t is x over a, but get rid of the cube, so cube root. And then sine t is x over a and cube root as well. So far, so good, everybody. And sorry, this is y. Okay. So we also know this cosine squared plus sine squared equals to 1. So then that's why here we have x over a 2/3 plus y over a 2/3 equals to 1. So actually, for this problem, we're able to express in terms of xy relation. Okay, let's make it look nicer. Then we have y to the 2/3, because you have both terms over a to the 2/3. We can multiply by a to the 2/3 on both sides, and this is what we get. Okay, and here are more examples. Okay, you have the butterfly curve. Okay, this is the x, this is the y, and this guy, does it look like a peach? And this guy, wow, beautiful. And this guy, do you think this guy look like a fish? It's a butterfly and fish. So far, so good. Okay, so on our course website, we actually have a GeoGebra project where you can plot parametric curve. Let me show you here. This is our course website. Under extra credit projects, GeoGebra project number 3. We can use GeoGebra to graph parametric curves. And this is the PDF instructions. Okay, you can download GeoGebra or you can use the online GeoGebra calculator. Watch this YouTube video, and then I provide you screen shots about each step, how to plot the parametric curve. Okay, so after you're done, yeah, this is a very easy project. After you're done, please share your project to public and generate a link. Please email me this link, then you will get 0.5% extra credits. Okay, so let's look at the first project. So this is the x and y. You can see, wow, it looks like a flower, isn't it? And you can see when your A increases, you're actually chasing out more leaves, okay, of the flowers. And then next one, let's see. We have the same one. Let me see. Okay, so you can see. So please be creative, and then you can create more interesting picture. Right? Oh, you can see this guy. It kind of, when it increases, it's bigger, 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 bigger. So we can generate a very beautiful picture. All right, let's continue. Okay, so what we have done, we have talked about the relationship between functions and parametric equations. So given a function, can you find the parametric equation associated to it? Okay, usually there are more parametric equations associated to the function, so you just need to find one. Okay, and given the parametric equation, can you find the function or xy relation that associated to it? And next, we're going to talk about calculus about parametric equation. So let's continue in video part B.